Do you want to know more about the glue that holds these molecules together? Well, I hope so, but if you don't, you're still going to learn it because there's going to be a test on it later. All right, well, it's time to learn about other types of glue, and I know you're excited, and I'm excited, so let's learn about this type of glue that we need to know about next.
Here we go. How come every time you come around my London Bridge wanna go down like London,
Forces! Forces!
How come every time you come around my
London, forces!
wanna go down like be going down like.
Okay, so for those of you that don't know, that's Fergie, a real hot thing back in the day. Everybody wanted to be like Fergie. Everybody wanted to listen to Fergie. Everybody wanted to see Fergie in concert. So depending on the year that you were born, you might not even know who that is, and you maybe never have seen that video before. And if you are one of those people, please do not tell me, because that's going to make me feel even older than what I do now. So we need to talk about how on earth is Fergie related to these forces, this glue, these molecular forces that hold these molecules together. Well, let me kind of tell you how Fergie is related. So instead of London Bridge, it's London dispersion forces. That's what we need to be talking about here. It is one type of force that holds molecules together. And sometimes we call them London dispersion, and sometimes we call them van der Waals. So we need to talk about van der Waals forces, and we need to talk about how van der Waals is related to everything, and what is London dispersion forces, but then at the same time, what are hydrogen bonds, what are dipole-dipole, what's ion-dipole. I mean, a couple of different, really handful of different types of glue that we could see in a molecule, and we got to know, okay, well, what are their definitions? How are they different? And how can I determine what is what? I mean, you know, those are the things that we have to do sometimes before we go into this. Now, once more, we're simply doing this to get an idea of what these physical property tests are going to entail later on when we actually talk about those. So let's kind of first talk about London dispersion and really discuss what on earth is this. It seems like this is maybe one of the trickiest types of forces that people just simply do not understand. Maybe it's not presented in the proper way. Maybe it's just something odd that, you know, they're like, oh, that's kind of weird. I don't really understand what they're trying to say. Blah, 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 blah. Okay, so here's the way that I like to describe London forces. All right, so here's a molecule. All right, I don't really care what it looks like. You know, this looks almost like a little turd. I don't know, but I'm just telling you this is a molecule. All right, let's call it a cigar instead. So here is a molecule, and this molecule, it almost maybe could look like a little South Park character, right? I think I have seen this on South Park before. So I need you to imagine this molecule. I need you to imagine this molecule, and this molecule is going to have little electrons in it. And we talked about these electrons, why they're there, and these electrons are negatively charged. And you know, these electrons can be anywhere they want to in these atoms. So that's kind of how the atom's made up. So I'm going to draw a circle of an atom up here at the very top. And then here in the center, that center is going to have our protons and our neutrons. So our electrons are on the outside, and these electrons are all the way around, all the way home. All right, so those electrons are freely moving. They are not stagnant. They can move anywhere they want to move. And that also means that when these atoms come together, those electrons can continue to move. So with London dispersion, what goes on is that these electrons are all the way around these molecules. And then at some point in time, randomly, so that's the key word, random, at a random time, and just statistically speaking, there is a option or an instance where the electrons can actually become lopsided just because of they're all over there, just randomly over there. That's just the way they are. Those electrons can randomly move to one side. And when they do, the molecule becomes lopsided. So the molecule, I use a squiggle. So squiggle, negative, and squiggle, positive. Those partial positive and partial negative charges, they are random, but they are also temporary. And the reason that they're temporary is because the electrons will continue to move. So what happens here is that within what we call the intermolecular forces, these are forces that happen between molecules now. All right, so this molecule, there we go. And this molecule, two molecules side by side. This molecule maybe is a covalent bond on the left and covalent bonding on the right. I mean, that's not what we're talking about anymore. What we're talking about is the bond or the glue that holds multiple molecules together now. All right, so with London dispersion, at a random time, that molecule can see electrons flying and zooming, and they're on one side of the molecule, making this a negative area. And when that happens, the molecule's neighbor is like, oh no, God, did you see who moved in? They're awful. They're all so negative. They always complain. They always think that this place is not good enough from where they came from. They can just move back home for all I care. Well, because it's negative, this gets a reaction out of the other neighboring molecule, and we can have a slight promotion of the opposite charge. So these negatives and these negatives, they hate each other. So that forces those negatives on that side, making the left-hand side of this molecule positive. All right, opposites attract, in other words. That's what's happening. So this molecule became negative temporarily, randomly on that side, and that promoted that molecule to shove its positive charge on the left-hand side, so that way they can hubba, and make some bonding in between. And this is the London dispersion force that begins to take place. So this is a I-N-T-E-R, molecular force, and that is the first intermolecular force that we are going to be talking about. So here's a diagram of what we just discussed. So London dispersion forces, step number one, we get a symmetrical distribution of electrons. So here the electrons are all scattered. They are all evenly spaced around the atom. And that's just normal. That's kind of how it is. That's the way they want it to be. Because again, if they are the same charge, they will hate each other. Opposites attract. Keep that in mind. So what will happen is that sooner or later, the electrons can become lopsided. And when those electrons become lopsided, what you will see happen is that there is a charge distribution now. So a negative area begins to form over here on the right-hand side of atom number 1, and a positive is left behind to the left-hand side of atom number 1. Well, atom number 2 is nearby. It's the neighbor. So with atom number 2, we can actually see, all right, well, that one's affected now as well. So that negative area is attracted to that positive area, and that little dashed line right in here, that dashed line is what we call the intermolecular force. All right, so that is one type of intermolecular force that we can talk about in this world of glue that we have now stumbled upon. So number 1, London dispersion, we have already discussed. So now we need to take a look at what a hydrogen bond is, what a dipole-dipole is, and what a ion dipole is. I will say that out of the choices that begin to take place, the London dispersion, because it is random, because it is temporary, is often the weakest of this category. Now, it depends on whose definition you're talking about, but London dispersion at its face value is often regarded as the weakest of the grouping that we will see here. Even though maybe London dispersion has a little bit more sticky glue between them, what will happen with hydrogen bonding is that there's so many of them that begin to take place, it overwhelms it. Hydrogen bonds are also very weak, in other words, and on its own, one little hydrogen bond is super, super weak. But when one is located, there are probably millions that's located there, and it is additive. It's cumulative, so it begins to add up. So London dispersion, though, not quite the same. London dispersion is often regarded as the weakest of the bunch. All right, so now let's talk about hydrogen bonds. What is a hydrogen bond? All right, so that's next on our list. And if you tell me hydrogen bonds is the bond to a hydrogen, wrong. That means you didn't pay attention. That means that you have no clue what you're talking about. You are using the name in order to define it, and that's not how this is supposed to work. So a hydrogen bond, what is a hydrogen bond? It is a hydrogen that is bonded to a nitrogen, an oxygen, or a fluorine. That is the part A of the definition. Now that's only half. So we have a part B of the definition, and it is attracted to another NO or F, and that means on another molecule. All right. So here we have a molecule, there we go. And here is a nitrogen, and let's say that nitrogen has a hydrogen on it. Ting, ding! First half of the definition is met. And then let's say that we got the same molecule over here, and that has a nitrogen on it as well. What we will see is hubba, hubba, hubba. And that hydrogen that is attracted to that or attached to that NO or F is going to be attracted to another NO or F, that's an N, another NO or F on another molecule. That is the second half of the definition, and for some reason, people will define a hydrogen bond as a hydrogen attached to something. No, it is not. It is a nitrogen, oxygen, or fluorine attached to another nitrogen, oxygen, or fluorine. That is what we are after here. This, folks, is the hydrogen bond. That is the hydrogen bond that we're taking. This hydrogen and that nitrogen. Hydrogen is a nonmetal. Nitrogen is a nonmetal. So therefore, that is a covalent bond that is connected there. That is a intramolecular force. That is something totally different. That is not what we are talking about here. A true hydrogen bond definition is a hydrogen that is attached to a NO or F. Ding, ding. This meets that. That is attracted to another NO or F on a different molecule. Now, this can be the same molecule or it can be a different molecule. It does not matter. And the reason is because the only criteria is that it has to have a NO or F. That is it. All right, so let me draw another molecule, and off of this molecule, let's say I have a nitrogen with a hydrogen attached. All right, now this is not the complete molecule. I'm just giving you an example. It's not a big deal. And then let's say that on this molecule, this is something totally different. Let's say there's just an oxygen that's sticking out here. Again, it is not prim and proper. There's no real such thing as a turd with oxygen. But it demonstrates the idea of a hydrogen bond. So in this case, hydrogen was attached to a nitrogen, and neighboring molecule, because it probably has tons of identical molecules around it, also has a nitrogen. Very common. It's okay. Not a big deal. But they can be different too. So this molecule is different. It has an oxygen that's hanging out. Not a big deal. Hydrogen attached to an NO or F. Ding, 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 ding. First half of the definition is met. And it is attracted to another NO or F on another molecule. Ta-da! Second half of the definition has now been finalized. And that, folks, is the hydrogen bond that we are referring to. So the molecules can be different. The molecules can be the same. I don't care. The molecule doesn't care either, because the basics of the definition is just that. All right, so here's an example of another hydrogen bond. Here we have a water molecule, and that water molecule is H2O. Oh, look, there it is. And that is a hydrogen that is attached to an N, an O, or an F. Ding, 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 ding. First half of the definition has been met. And then it just so happens that another water molecule is nearby. And they're like, hey, buddy, guess what? I've got this hydrogen attached to an NO or F. I know you want it. Come and get it. And that molecule says, oh, yeah, you got a point. I do want it. So this hydrogen that is attracted to or attached to an NO or F is now attracted to another NO or F on another molecule. And that little dashed line right in between them, that, folks, is the hydrogen bond. That is the proper definition of a hydrogen bond in a roundabout way in Tracy's terms. So hopefully that makes a little better sense. Next up, if we take a look at our intermolecular forces, also known as IMF, intermolecular force. The next thing that we're going to talk about is this idea of a dipole. Oh, okay. So what is a dipole? That was something else that was kind of below hydrogen bonds. And this is what a dipole is. Here's a molecule, and that has a positive and a negative end. And these are not temporary. These are not random. It is the way it is. That's the way the molecule is built. It is a permanent charge or partial charge on one side or the other. And then here is another molecule that is also permanently charged that way. These two molecules will align up so that opposites attract. Oh, hubba, and we get a little bitty bond that forms between the positive and the negative. That area, this area, is a bond. It is glue that holds different molecules together, and this glue is a dipole. So the word di means two, and pole is like polar sides of a magnet, polar sides of the earth. These are just charged areas, either positive or negative. So there's two charges that are on these molecules. It is a permanent charge where one side or half is positive and the other side or half is negative. So when we get two molecules, again, they can be the same or they can be different. It does not matter. But if two molecules come together and they are by definition a dipole, then one little dipole falls in love with the other little dipole, and that is glue that begins to hold them together. So here is an example of a dipole bond that can be glue that holds molecules together when we begin to do these physical property tests. So here what you're seeing is a HCl. This is hydrochloric acid. And the hydrogen side is a positive, and the chloride side is a negative. It is that way. It is built that way. That's how the charges are. They do move around freely, but they do move around in the same playground, and they don't really leave those areas of the molecule. So that negative, that chloride piece, that's always going to be negative, and it will not become positive. The hydrogen, it will always be positive. It will never become negative in the way that this molecule is built. That is called one of the dipoles, right? And then another molecule, and in this example, it's just exactly the same thing. It does not matter. It's just a different dipole or the same dipole. By definition, if it's a dipole, it will work. Who cares what it is? But there is a permanent positive and a permanent negative charge on these molecules as they start to assemble. So the negative area and the positive area come together, and that dashed line is right there. And that dashed line is going to be called the dipole glue or bond that holds these molecules nearby, so that way when we grab them, when we use them, when we test them, it is an intermolecular force that we have to overcome. Guys, and finally we have an ion dipole intermolecular force, and this is just the same as before. A dipole is a molecule, and that molecule has a permanent charge that is a separation of positive and negative. And then an ion is not really a molecule. An ion is just a charged atom. An anion is negative, a cation is positive. So this is just an atom from the periodic table, one of the little Lego blocks that make molecules, but it's just a Lego block. So the Lego block that's either positive or negative is attracted to a dipole, which is partial positive or partial negative here. So that attraction that we see between that ion, either anion or cation, and the dipole molecule, that is the ion dipole bond. So now that kind of sums up our intermolecular force and our intramolecular forces. So intra is within the molecule, and inter is amongst the molecules, more than one. So in the next video, we will talk about our first physical test that we need to talk about, and that is our melting point test. So in the next video, we'll talk about what melting point is, some things that we need to take away from that, and how to actually perform that test in a laboratory. So how can we overcome these inter and intramolecular forces in order to get a melting point from that state of matter? That is what this is all about.